I know that your definition and my definition of cool are different, but I think related rates are actually really cool. Related rates are something that applies calculus and applies Calc 1, because a lot of times calculus can't be applied until we're into like the 3D space, and so sometimes you feel like you're learning all this calculus and you can kind of apply it, but it's hard. And so this is so cool. Okay, that was too many so's. Anyway, related rates. Basically, what a related rate is doing, it's a story problem, and we're trying to find the rate of change with respect to time of some quantity by using the related rate of change of a related quantity. So maybe we're trying to find the rate of change of the volume of something if we know how fast the height is changing. Or maybe we're trying to find the rate of change of the height if we know how much the volume is changing. So we're trying to find the rate of change of one thing if we know the rate of change of other things. Related rates are always with respect to time, because they're rates, so things are always happening with respect to time. So here's basically how we do it. We draw a picture, if you can. I always draw a picture. And we choose variables for all the unknowns, okay? Then we write what we're given and what's to be found, and then we use dt symbols, meaning if we're trying to find the rate of change of the volume, we would say dv dt. If we're trying to find the rate of change of the area, it would be dA dt. Then we write an equation relating the variables. If a quantity is changing, this is super important. If a quantity is changing, it has to be represented with a variable. If a quantity is constant, it has to be represented by a number, okay? So if we talk about, like, say we're talking about a cone, oftentimes these talk about water draining out of a cone shape vessel of some sort. So we have this water draining out, and the height is changing over time, so that needs to be a variable, okay? Can't think of something that the radius is also changing in that situation. Lots of things are changing in that situation. But if something is not changing and it's constant, it has to have a number. So we're going to put the number in before we differentiate, and you'll see that. Then we implicitly differentiate with respect to t. We're always differentiating with respect to t because t is our variable. T is the independent variable that is changing over time. Have I highlighted it enough? We are always differentiating with respect to t. Okay? And then we substitute in number values and we solve for what we're looking for. So some things that you're going to need are these geometry formulas. Typically on the AP test, if you need this formula, they will give it to you. And in all of our tests, I believe, I always give you those formulas. If for some reason on a test I forget to give you the formula, you can let me know and I will give you these formulas. I don't want you to fill your brains with these formulas and not have room for calculus. There are some of them that, like, and you may not be given, okay? Like a squared plus b squared equals c squared to find the sides of a right triangle, the area of a triangle, 1/2 base times height, area of a circle, circumference of a circle. So these ones, I feel like these ones are ones that you actually probably should know and are ones that you may not be given on the AP test because they're very, very simple geometry formulas. All the rest of them, oh, and this. Length times width is area, and perimeter is twice the length plus twice the width. Okay. So in these first problems, the first steps are given to us. The first steps are already done. They don't give us the word problem. We don't have to solve the whole thing. We're just going to see what this implicit differentiation actually looks like with respect to t. So I'm wanting, I know that area equals side squared, okay? So this is looking at a square because area equals side squared. I know that the rate of change of the side with respect to t is 3, meaning the sides are changing at a rate of 3. And I know that the side, at the time I'm trying to find it, the rate of change is 4. So let's think about how we're going to differentiate this. First things first, we want to write the equation relating the variables. Well, we already wrote that. So now you might be tempted to put 4 in here for S because you're like, oh yeah, S is 4. But is it always 4? No, we're talking about S changing over time. So S needs to stay a variable because it's changing. This is information we're going to come back to later and use, but right now S is changing, so it stays a variable until after we've differentiated. So we differentiate both sides. So we have the derivative of the area with respect to time, which is just dA dt, equals the derivative of S, which would be 2S. But see, it's implicit where with respect to t. So anytime I don't differentiate t all by itself, I need to tack on that implicit hook on, right? So this is 2s ds dt, okay? Now I'm trying to find dA dt, right? How fast, this means how is the area changing with respect to time? So I differentiated it. I already have dA dt by itself, and I actually know some of this information. It says the rate of change of the area equals 2 times the side length at that moment times the rate of change of the sides. Okay? What is the rate of change of the sides? Well, it's 3. So I know dA dt equals 2 times S times 3. So I'm going to put that 3 there first, and then I'll explain why I'm putting S in now. Because now we're trying to find the area at the exact moment that S equals 4. So now I'm going to put the S in. And dA dt, when S equals 4, is 6 times 4, which is 24. So the rate of change of the area with respect to time is 24 when S equals 4. Whew, it's a lot of information, isn't it? Here's another one. We were given a lot of information and we want to find dy dt. So first, dy dt means how is y changing with respect to t, okay? What is the rate of change of y with respect to t? So first, we always start out with the equation of how x and y are related. That's this right here. In future examples here in a few minutes, you're going to write this equation yourself. But right now, it's been given to us. So we say, okay, x and y are related, that x times y equals 12. And then all the rest of this stuff is just information that I'm going to use here in a minute. Now I need to find the rate of change of y with respect to t. So you notice that this is a product. So I'm going to use the product rule. So I have x and y. What is the derivative of x with respect to t? This is tricky because the derivative of x normally in the past has just been 1, right? But we're not differentiating with respect to x. We're differentiating with respect to t. So this is dx dt. So the derivative of x with respect to t is dx dt, or x prime. But in this case, let's write dx dt because it's a little bit more precise. So we're writing dx dt, and what's the derivative of y with respect to time? dy dt. That means the derivative of y with respect to t. So now I do fig plus gif. Fig plus gif. It doesn't really matter because, you know, associative property and all that. Okay, so dx dt times y plus dy dt times x. And then we differentiate the other side as well. The derivative of 12 is 0. Now we got to get dy dt by itself because that's what we're actually looking for, right? So we subtract and we have dy dt times x on this side equals negative dx dt y. And we can, let's divide by, I don't know if I want to divide first. I think it's going to be too messy to divide first. So don't stress about getting dy dt all by itself. We can start plugging in numbers right now. Okay, so what do we know? We're looking for the rate of change of y, and since y was changing, we had to leave it out. We couldn't put this 4 in here at the beginning because 4 is only what y equals at a certain instant. Y is changing over time, so we have to leave it as a variable until we're all the way down here and we can finally plug it in because It's no longer changing because we're looking at the rate of change at that instant. Okay, so when y equals 4, so we're going to plug that in. So we have dy dt x equals, and then dx dt equals -6, so that's 6 times 4. So dy dt x equals 24. And now what? Because dy dt still isn't by itself, but they didn't give us an x. But they did tell us how x and y are related. As x changes, so does y, right? So when y is 4, what does x have to be? Because x and y are changing. This is an inverse relation. But they're changing, right? And so when y becomes 4, what does x have to be? Well, it has to be 3, right? So when y equals 4, x has to equal 3. So now I know what that x is going to be down here because I know how x and y are related to each other. So that's going to be 3 equals 24. Therefore, our final answer, now that we can finally get dy dt by itself, is 8. That means the rate of change of y with respect to time is 8 when y is equal to 4.